Hi everyone. Today we're going to be determining a necessary criterion for planar graphs. And by contrapositive, that means we're going to be finding a sufficient criterion for non-planar graphs. So let's say we're dealing with a connected planar graph with greater than or equal to 2 edges. So that's our condition. I'll draw an example for you, one that looks, for example, like, let's say we have a shape like this one, and we have another piece to it here, and we have this sticking out here, and this sticking in here. So we've got a few components here. What I want to first show or define is that we have faces. So we have one face here, and we have another face here, and we also have on the outside we have the unbounded face. So we have 3 faces here. What I want to talk about is the degree of a face, which is a less common definition than the degree of an edge, but we're going to need the degree of a face. Before that, I'm going to define 2 kinds of edges. So edges can be one-faced or two-faced. An edge is one-faced if it's adjacent, so it touches one face. And it's two-faced if it's adjacent to 2 faces. So in this case, we have that this edge is one-faced and this edge is one-faced, whereas all the other edges are two-faced. Now, for the degree of a face, there's a couple of equivalent ways of defining it. What we do is that we add up number of edges traversed on a cycle through the boundary of the face. So for example, up here we would do 1, 2, 3, 4, 5, and here's the tricky part, 6 and then 7. So this face has degree 7, even though there's only 1, 2, 3, 4, 5, 6 edges. So as you can tell, this is equal to the sum of 2's for one-faced edges plus the sum of 1's for two-faced edges. So that's how we're gonna equivalently define the degree of a face. Now the next thing we're going to explore is the sum of all the degrees of all the faces, including the unbounded face. So f in big F, where big F is a set of faces, and we're going to take the degree of f. See, this one, it's actually equal to 2 times the number of edges. So capital E is the number of edges, because here's what happens. We have one-faced edges contribute 2 to one face in this sum, and two-faced edges contribute 1 to 2 faces. Well, these are both to the degrees of those faces. So in the end, we just end up with 2 copies of each edge. with the number 1 being contributed by each copy. So that's our first identity. The second thing, which I'm not quite going to prove, I'll just outline it, is that the degree of a face is always greater than or equal to 3 in a planar graph that is connected. The reason is that we can divide it into two cases. First of all, one is that the face is bounded, or the face is unbounded. In the bounded case, it's clear that this is true because you need to have at least a triangle, if not a square or a pentagon. And so on. So the bounded case is easy. The unbounded case, there's two cases here. One is that it's a tree, and the other case is that the graph has a cycle. In the cycle case, it's clear by the previous reasoning that there has to be at least three things in the boundary of the unbounded face. And in the tree case, there has to be at least 2 vertices. So we end up getting 2 times 2 is equal to 4, like this. 1, 2, 3, 4. For a 4 degree of the unbounded face. So that's the outline of that proof. So what we're going to be using is that the degree of f is greater than or equal to 3. Now combining it with this part here, what we get is that 2e is equal to the sum of the degrees of the faces in capital F, and this over here is going to tell us this is greater than or equal to 3 capital F, 3 times the number of faces. So we're getting close now. What we find is that by the Euler formula, v minus e plus f equals to 2 for planar graphs. So that combined together tells us, well, first of all, we're going to isolate f to get f equals to 2 minus v plus e. And we're going to put this in here to get 2e is greater than or equal to 3 times 2 minus v plus e. And that's equal to 6 minus 3v plus 3e. And finally, we can simplify this to get that 3v minus 6 is greater than or equal to e. So this is a necessary condition for a planar graph. And notice that this thing here is independent of a particular planar embedding. So let's apply, because it's independent because it only depends on the vertices and on the edges, the number of each. It doesn't depend on f. So I'm going to apply this to a graph called K5, which is it looks like a pentagram of some sort, where we have a star and we have a pentagon around it. This is the complete graph on 5 vertices. So the number of vertices is equal to 5, and the number of edges is equal to 10. And we find that 3v minus 6 is equal to 3 times 5 minus 6, which is 9. And 9 is less than 10, which is equal to e. So this criterion does not hold, and this is connected because it's a complete graph. So that means it is not planar. There is no planar embedding of this graph. So that's an example of us using this criterion. Thanks for watching, and I'll see you next time.